Hello and welcome to video 3 in our series on examples from section 10.4 of our calculus text. This one I want to talk about the alternating series remainder estimate. Work a couple of examples. And so this is something that we'll see in this section, but also coming up toward the end of the chapter as well. And just a reminder of what this says is that if you've got an alternating series that converges, then the remainder, which we want to recall is the sum of all the terms involving from capital N plus 1 outward, that happens to be less than simply the n plus first term in the positive series that's used to formulate the alternating series. And so our steps are going to be to identify b sub n plus 1, set it less than the amount of error that we're willing to accept in our estimate, and then solve either through some algebraic means or even occasionally with some trial and error. So we want to remember the point of this is if we were to make b sub n plus 1 less than, say, whatever our error is, but in this first example it's going to be 1/10,000th, then because of this inequality where the remainder is less than b sub n plus 1, we want to keep in mind that we're also making the remainder less than 1/10,000th, which is really what our goal is. So by keeping the n plus first term less than our desired error, we're making sure that the remainder is less than our desired error. So we've got two examples. One involves the series that we've talked about in our first two videos for these exercises, the alternating series summation -1 to the n plus 1, 1 over n cubed. And so we start by observing that b sub n is 1 over n cubed. So b sub n plus 1 is going to be 1 over the quantity n plus 1 cubed. And so our goal then is to make 1 over n plus 1 quantity cubed less than 1/10,000th. Because if we can make b sub n plus 1 less than 1/10,000th, we're making the remainder less than 1/10,000th. Well, if I take reciprocals, I change the direction of the inequality. So my goal is to make n plus 1 quantity cubed greater than 10,000. To find what n is, I can then take the cube root. That's approximately 21.5. And so we want n to be bigger than 20.5. So we'll take capital N to be the smallest one that works, 21. And so what we're saying then is, if we just add up the terms 1 through 21, -1 to the n plus 1 times 1 over n cubed, this is going to, for sure, approximate the entire infinite sum to within 1/10,000th of its actual value. It turns out we can actually take fewer terms, but this is the one that our remainder estimate guarantees will work. Our second example is going to be to look at a different alternating series, and we want to approximate it to within 1/20,000th of its actual value. Summation n equals 1 to infinity. Actually, I'm going to make that 0 to infinity, -1 to the n over n factorial. We'll encounter this series again in a later section of the chapter, and we'll actually go back and talk about what the actual sum is. We can actually figure this out. But for the moment, I'm going to let or observe that b sub n is 2 to the n over n factorial. So b sub n plus 1 is going to be 2 to the n plus 1 over n plus 1 factorial. So my goal is to find capital N so that 2 to the n plus 1 over n plus 1 factorial is less than 1/20,000th. I like making numbers bigger than a number rather than trying to find numbers that are smaller than a number, so I'm going to still take the reciprocal of this, and so I want to find n plus n so that n plus 1 factorial over 2 to the n plus 1 is greater than 20,000. And unfortunately, I don't know of a better method to work with in this case than just trial and error. So there's no algebra that we can do to reduce a factorial, and so we're just going to have to pick something and see how it goes. When I was working this problem, I started by looking at, well, let's just try n equals 8. And so when I calculated 9 factorial over 2 to the 9th, I got 708.75. And let me just take a second to remind you of how to get a factorial on a TI calculator. You're going to push the math button, and then you're going to toggle over to the probability menu under the math button, and option 4 is the exclamation point, which stands for the factorial. So math, then go to the right until you get to the PRB menu, and then option 4 will be your factorial button. Well, back to our work here. When n was equal to 8, I got a number that was well less than 20,000. So I'm not going to step it up just by 1 and see what I've got here. I'm going to go up and go to 10 and see what 11 factorial over 2 to the 11th is equal to. So that's 11 factorial. And according to my research, I got 19,490.625. So close, but too far, but not good enough. So n equals 10 isn't going to work, but I feel pretty sure at this point that n equals 11 will do the trick. So 12 factorial over 2 to the 12th is way over 20,000. I got 116,943 3/4. That's the one that works. And so what I conclude is that if I want to approximate this convergent alternating series to within 1/20,000th, I'm going to stop with 11. So if I go from 0 to 11, that's going to approximate the sum from 0 to infinity to within 1/20,000th. I will point out that it's not initially clear at the moment that this series on hand converges. This is the sort of thing that we'll be tackling in the next section, but right now I'm just trusting you to believe for the moment that this is a convergent series. So this does converge. We haven't showed it yet, but we'll see how it does in upcoming sections. So now you can begin working on some practice exercises and some WebAssign.